Hello guys, let's consider a rotational motion where an object is moving in a circular form. Okay, so in this type of motion, we have an object that is moving, in a uniform circular motion, and we also have an object that is moving in a rotational kinematics. So rotational kinematics is when the object is speeding up or slowing down. Then uniform circular motion is when the object is moving at a constant speed. Okay, so usually when the object is moving at a constant speed, so we consider, for example, we can calculate, the speed using this formula with a relationship here between the radius and the period. And we can also consider formulas like centripetal acceleration and also a centripetal force. So we also have a lot of relationship with them using angular frequency and the frequency time in terms of period and frequency. Okay, let's consider the rotational kinematics formulas here. Okay, you can see we have the first formula then, omega final equal to omega initial plus angular acceleration times time. Okay, so these quantities are also described there in the right hand side. For example, omega initial is the initial angular velocity. Okay, so we also have some quantities there. For example, tangential velocity there, it is r omega, and tangential acceleration, it is the radius times acceleration, angular acceleration. Okay, let's consider our first question there. It says a high-speed train rotating at 2,400 revolutions per minute comes to a halt in 2.5 seconds. So the question is, what is the magnitude of the transangular acceleration? Okay, let's check quickly what is given here. Okay, as you can see, we're given the initial angular velocity here. We're also given the final angular velocity, which is 0 radians per second. So we're given time. Okay, so the first question, we want to calculate the angular acceleration. Okay, let's work it out together quickly. Okay, so let's see. We have angular velocity here, which is 2,400 revolutions per minute. We need to convert it into radians per second. Okay, so one revolution is equal to 2 pi. So it's equal to 2 pi. Okay, so we know that 1 minute is equivalent to 60 seconds. Okay, so let's work it out quickly. So the answer, it gives us 80 pi, which is the same as 251.33 radians per second. Okay, so the formula to use here, let's choose, since we have the initial. Okay, let's check. Final will be 0 radians per second, then time is 2.5 seconds. So we can also write this time as T final is 2.5 seconds, and T initial is 0 seconds. Okay, let's check now. Let's check the formula to use. So we can choose the formula to use from these formulas. Okay, let's check the formula to use here. So we can use this one, the first one. We can use the first formula here. Okay, so we can use the first formula. So we have omega final equal to omega initial plus angular acceleration times t. Let's make angular acceleration the subject of the formula. This is what we have. Then we can make substitution. So final angular velocity is 0 radians per second minus the initial is 251.33 radians per second. All over the time is 2.5 seconds. Okay, so let's work it out. What is the answer? Okay, the answer is negative 100.5. Write it in for significant figures. So radians per second squared. Okay, it's negative because the object is slowing down. Okay, let's go to the second question then. Okay, let's see the second question. Okay, so the second question there is to calculate how many revolutions does it make as it stops. Okay. So 6.1.2. So we're looking for the number of revolutions. Okay, so we can use this formula. Okay, so let's make substitution. Initial is 0 radians. Plus initial, remember we said is 251, comma, was it comma? Comma 3 or comma 33. That is radians per second. Time is 2.5 seconds plus this angular acceleration is negative 1, 0, 0.5 radians per second squared times the time, which is 2.5 seconds squared. Okay, let's work it out. What is the answer there? So the answer is 314.2625 radians. So we need to calculate it in revolutions. So we can multiply, we need it in revolutions, but we're given in radians. So we can multiply by 1 revolution over 2 pi radians. So radians cancels. So let's get the answer then. So we get 50 revolutions. Okay, that is the answer. Let's go back to the questions. Let me share the questions. Okay, so we're done with that one. Let's go to the next problem, 6.2. The angular velocity of a process control motor is omega equal to 20 minus 1 over 2 t squared radians per second, with t given in seconds. So the first question, 6.2.1, says, at what time does the motor reverse a direction? Okay, reverse a direction, we know it should reverse, at the turning point, where the angular velocity, of course, is 0. Okay, let's work that one out together. Okay, so this is 6.2. We're given this formula here, which is 20 minus 1 over 2 t squared, which is radians per second. So we can also write it as negative half t squared plus 20. Okay, so it reverses at the turning point where omega is 0. So then we're going to have 0 equal to half t squared plus 20. This is negative, so we can take this to that other side. It becomes positive. Then you can multiply by 2 both sides. Okay. To make t the subject of the formula. So you multiply by 2 both sides. Then you can take a square root both sides to make t the subject of the formula. When you take a square root, of course, you take plus or minus, but we know t is always positive. So what is the square root of 40 there? It's 6,3. 6,32. So we write it into significant figures. 6,2 seconds. Okay, let's go back to the questions. Okay, the second question says, to what angle does the motor turn between t equal to 0 second and the instant at which it reverses the direction? Okay, between t equal to 0 and t that you have calculated, which is 6,3. So let's answer this one together. Okay, so this is 6.2.2. So we know that the velocity is the rate of change of displacement. So which means angular velocity is the rate of change of angular displacement. Okay, so if we make angular displacement the subject of the formula, this is what we have. Then which means theta will be the same. If we take the integral both sides, we take it from 0 to t, where t is 6,3. Okay. But we know that angular velocity here is 20 minus half t squared. Okay, so we can substitute angular velocity by 20 minus half t squared. Okay, so dt. All right. We know that integration is what is commutative, so we can take the integral of the first term there, which is 20t from 0 to 6,3. So minus half. Okay, so we take the integral of t squared, which is the same as t to the power 3 over 3. We took negative half over 2 out of the integral as a constant. So this is also from 0 to 6,3. Okay. So now we can substitute t by this. Okay, let's work it out. So we have 20 times 6,3 minus 1 over 2, 6,3 to the power 3 over 3. Okay, what is the answer? So the answer is 84 radians. Okay, the answer is 84 radians. Let's go back to the questions. Let me share the questions. Okay. Yes, we've managed to answer that question. Okay, so please do this one now at home as an activity. 6.1 says, the figure below shows the angular velocity versus time graph for a particle moving in a cycle, starting from initial angular displacement equal to 0 radians at t equal to 0 seconds. So you can see the graphs there, given where along x-axis we have time in seconds, and along y-axis we have angular velocity in radians per second. Okay, the question is to draw the angular position versus time graph, include an appropriate scale on both axes. As you can see, also in the graph given there. You see, along x-axis, as you can see, you have a scale of 2 there, from 0 to 2. Also here from 2, so it's a scale of 2 seconds. Along y-axis, as you can see, it's a scale of 10 radians per second. So you need to use a scale. Okay, 6.2. Please, you need to do this by yourself. Sand moves without slipping at 6,0 meters per second down a conveyor that is tilted at 15 degrees. The sand enters a pipe 3,0 meters below the end of the conveyor belt, as shown in the figure. So you can see you have the sketch there given. What is the horizontal distance D between the conveyor and the belt? So you can see we're looking for this distance here that we need to work it out. Okay, that is D. Okay, so that distance there. So 6.3, a computer hard disk 8,0 centimeters in diameter is initially at rest. A small dot is painted on the edge of the disk. The disk accelerates at 600 radians per second. Okay, 2. Okay, that is, I think this must be, let's cancel this. It's like that. The disk accelerates at 600 radians per second squared for 12 seconds. Okay, for 12 seconds. Then constants at a steady angular velocity of for another 12 seconds. So 6.3.1, what is the speed of the dot at t equal to 1,0 seconds? Through how many revolutions has the disk turned? Then the last question, 6.4, is a cubine is spinning at 3,800 revolutions per minute. Friction in the bearings is so low that it takes 10 minutes to coast to a stop. How many revolutions does the cubine make while stopping? Okay, please do that for yourself. Okay, that is the end of this lesson. Okay, thank you.